All right, let's take a look. I see a lot of good setups. I think we're right there. Let's go through the calculations here. So I'm going to start by finding my x center of mass. That's just where I'm going to start with. I have a formula I can start with. Center of mass is just a weighted average. It's taking my mass values and weighting them by some distance value. And I'm going to divide by the total mass. That's the process. So in this case, I just got to find out what a little slice of mass is. So to find the x center of mass, I'm going to slice vertically like this. And I just want to find the mass in the slice. Well, I have a density of kilograms per meter squared. If I want to end up with kilograms, I got to multiply by something meter squared. I got to multiply by an area piece. So this should be density times some sort of area element. My density is 5. My area element, well, here's my little slice of area. The height here is going to be x squared, and the thickness is going to be delta x. So it looks like I have 5 times x squared delta x. And then I just put these values in. I got the integral of x times 5x squared dx divided by the integral of 5x squared dx. Integrating from where to where? 0 to 1. All right. Now I can actually pull both of those 5s out. Those 5s are just constants. I could take this 5 and pull it outside of my integral like this. I could pull this 5 outside of my integral like this. And then because they're outside of the integral and they're in a fraction, I can just cancel them out. So really in the top, I'm integrating x cubed. I get x to the 4th over 4 from 0 to 1. In the denominator, I'm integrating x squared. I get x cubed over 3 from 0 to 1. I plug in these values. Looks like I get 1/4 divided by 1/3. And when I flip and multiply the bottom here, it looks like I'll get 3/4. How does that look? Yep, good. And once again, we want to make sure this makes sense. If this is my object, and it's distributed homogeneously here, where it's a constant density, it's not more dense in one area than the other, then just because of the area, I expect my center of the mass to be on this side. There's more stuff over here. So if I had to balance this, I'd expect to have to move my finger over here somewhere. So 3/4 makes sense. I expected a number somewhere between 1/2 and 1. All right, now I got to do the y center of mass. I have to get this point, this coordinate for the center of mass here. So I do the same formula essentially, y dm and integral of dm. But now in this case, a slice of my mass will be a little bit different. I have to cut a different slice. Instead of working with this slice, I'm going to work with this horizontal slice now. So I'm trying to find the y center of mass. And I'm going to cheat a little bit. I'm going to go like this. Now that integral will be different, but the result should be the same because that denominator is just the total mass. And the total mass isn't changing here at all. That makes sense? All right, but the numerator I do have to recalculate. So I look at that numerator value, and I'm going to, once again, find the mass just in my slice. And once again, this is my density times the area of the slice. But what is the area of the slice in this case? This value times this value. What are those values? A little louder? 1 minus the square root of y, delta y, and I had my density up front here. Any questions about that piece? That square root of y represents the distance from the y-axis over to the function, and I want 1 minus that distance. Any questions about that piece? All right, I got 1 minus this piece. All right, so that's my value here. I will throw that into my integral. I'm integrating y times 5 times 1 minus the square root of y dy from 0 to 1. A different 0 to 1, but still 0 to 1. Right? Instead of dividing by a fraction, I'm going to flip and multiply. I'm also going to pull out my 5 here. I will get 15 times the integral from 0 to 1. I'm going to distribute that y as well. And I will get y minus y to the 3 halves. I'll pause there to make sure we're on track with that one. Did a couple steps there at once. Any questions there? All right, so now I got 15 times, looks like y squared over 2 minus y to the 5 halves divided by 5 halves, or times 2/5, 0 to 1. It looks like I got 1/2 minus 2/5. All that stuff, of course, minus 0. I shouldn't take that for granted. Sometimes I evaluate it at 0. I do get values, but in this case, I don't. And then I want to put them over a common denominator. Looks like I will have 5 minus 4 all over 10. So it's like 1/10. Uh-oh. This would give me 15/10. I'm not happy with that answer. I must have messed something up along the way. Let me see where my mistake might be. No, absolutely not. In fact, I don't believe it comes out to be 3/4. The action past 1/2 is different than the action before 1/2. Think about it in other intervals. So we can't chop up intervals because it's not a linear function. So the action from 0 to 1 will be different than the action from 1 to 2. And it will change much more dramatically on the right half than on the left half. So I made a mistake somewhere, so we got to see if we can find it here. Does this look good for an integral? Yep. 5 times 5 is 25. That's true. Where did I do something different? Right here? Yeah, square root of y. So other than sloppy writing, I must have some other mistake in here. Oh, yep, you're absolutely right. So I got an extra factor of 5 here. So those 5 should have canceled out. So I should have this out of here. Absolutely, thank you. So that was my mistake. I should not have this 5 out, or I should have an extra 5 in the denominator for my mass. So that was my mistake. So I have an extra factor of 5. That makes this 3, this 3, this 3, this 3, and then I get 3/10, which I believe is the correct answer. Yes. And it makes sense visually because I'm expecting a number between 0 and 1/2. I expect it to be on the lower end. So I guess that's another reason we can say right away that it's not going to be 3/4. All right. Does it make sense why we expect an answer less than 1/2? I mean, if we chop this right at about 1/2 into little quadrants, I would expect my center of mass to be down here somewhere. Yep. 1/3 here. Okay, so my formula says a weighted average, x times mass divided by the total mass. Same thing here, y times mass, but still divided by total mass. So this value is the same in either case. So once I've done the work up here to get some sort of value, which I ended up to get 1/3, then I can just say that's my total mass. And in fact, I really should be a little more careful because my total mass isn't 1/3. It is 5/3. That was my mistake. But there was a 5 to cancel from the numerator as well. So basically, I'm just pulling this known value down here. Does that make sense? Okay. And we could recalculate it, and the integral would look different. The integral would not look like this. The integral would look like this, except without the y. It looked like 5 times this thing. But if we integrate it, we would still get that same value in the denominator. Does that make sense? Okay. You have a question? I mean, you just have to decide what to do, and you have to be more careful than I was, apparently, right? So I guess in hindsight, now that I realize what I did there, I would probably have not canceled my 5s and left them there, and then I would have just left my 5s in here, like this, and then maybe cancel them in that next step. So I can see that value for the total mass a little better. So yeah. Okay. Other questions? All right. And the result is a point. It is the point 3/4 and 3/10. And that's where you put your finger to balance the plate, right? So amaze your friends. Grab a plate at home. Calculate the center of mass. Okay. All right. All right, so now we are going to get into 8.5 a little bit. I have one more problem from 8.4 that I want to look at. After that, I'm going to open up for questions if you have some. But the next problem I want to do is this pyramid problem. So I have a pyramid here, and it's filled with smoke. Oh no. The thickness of the smoke, sort of a density of the smoke, is given to us as this function, H minus 15 grams per cubic meter, and it starts at a height of 15 meters from the ground. So they're telling us a couple items here. They're telling us they are measuring H from the bottom. That's the first thing they're telling us. They're giving us a density, and all the dimensions are on there. Find the total mass of smoke that's in the pyramid. All right, see what you can do here. Once again, I want to see whiteboard work. Whiteboard work tells me that two people are looking at it together. There's less likely to be a mistake. There's more likely to be discussion about what we're doing. Just fold out here. You could get each girls to work together, maybe. Some work on a whiteboard. Talk collaboratively. Thank you. You two gentlemen could work together collaboratively to discuss common problems. Shared workspace. I know a lot of times we want to have these problems in our notes also, and so it's the whiteboard and the notes, but since you're already probably all recopying your notes, every evening already, one thing you could do is just take a quick picture of your whiteboard, and then you could just copy that over instead when you're done. So. All right, let's take a look at some of the work on the board here, see how we're doing. All right, so this is what I came up with, the final integral here. How does this thing look? Let's talk about some of the pieces here. I start off, I'm trying to find the mass of the smoke. Can't do it all at once, I got to cut a slice. So I draw my little slice right there. And then I'm just trying to find the mass in my one slice. So there's my process, the mass in one slice. If I have a density that's grams per cubic meter, and I want to find out the amount of grams, I just take my density times the volume. So I got density times volume. And then I'm just working on this volume problem that I did in 8.2 or 8.1, right? The volume of the pyramid. So we said that was L squared, the length of one of the sides of my slice. When we first did this problem a couple sections ago, we did length times width, but then we said it was a square base, so that those values should be the same. So I get my area of that square face times the thickness of delta H, that gives me my volume. So now I have this expression. Any questions about that so far? So the total mass is going to be integrating that piece. Density is a function I can plug in. Now my only problem is I got to find L in terms of H. How is the width of that slice changing as I go up and down my pyramid? Well, I do my similar triangle thing. So I draw this big triangle inside of the pyramid, and then the smaller triangle that's just going through my slice. I put my ratios in here. Very important that I'm using this as my height of my triangle. I don't get to choose in this case. I can't choose to count H coming from the top bottom because that will mess up my density function. My density is defining what H is. Right, so I can't flip it around here. Right, so I set up my similar triangles. I write my equation. I solve for L. Any questions about that step? These steps here? Once I get my expression for L, I'm pretty much done. I just chug everything in there. All right, I have my density piece. I have my L squared, my DH, integrating from 15 to 50. From 15 to 50. Because that's where my smoke starts, apparently. Any questions about that? What will happen if I integrate from 0 to 50? Yes, bad things, right? Because I will get negative smoke densities, whatever that means. It's not like it will just be 0 below there. It will be negative weird stuff below there. So it will totally mess up my problem. Okay. All right, any questions about this problem? Nope. Anybody got on a calculator? Anybody check this one out? It's not really that hard to do. I mean, really, the best way to do this would just be to expand this thing out and then multiply through by this. You'll get a third-degree polynomial, so it'll be a power rule 3 times. But just for the save ourselves a little time, I will just chug it out real quick. All right. Let's see what we got here. We got the integral from 15 to 50 of h minus 15. 20 minus 2/5 h quantity squared with respect to h. $20,000 grams. You know, Mathematica wants to give you exact. They don't want to round. They think mathematically, not engineering, right? So if I just do this, it'll give me the exact answer with this fraction. Now, if I want a decimal representation, I just put a decimal in. Put a decimal in, you get decimal out. Or, of course, you can use that command to give you a numerical output. Other questions? Yep. Absolutely. Let's take a look at 13 from the homework. All right, so I'm going to work it from the book. Is that all right? Okay. Trying to make sure it wasn't like an input question. Ah, yes, my garbage incinerator question, right? All right, so we are told that we have a garbage incinerator and it's spreading out soot. So I think of this almost like a smokestack problem or a volcano problem. I have this thing in the middle and it's kicking out soot into the air, and all that soot is then raining down at different spots over here, but more is going to be closer to the thing and it's going to be smaller out. So if we think of maybe a cross-sectional piece, the depth of the soot is going to look something like this. And it's going to be a little bit deeper, closer. It's going to get less deep, farther away. Okay? Now that's like the side view. The top-down view would say, here's whatever my garbage incinerator is kicking out the soot, and I'd be looking at, different levels at different distances away. But for every spot that's the same distance away, everywhere around this circle, I should expect the same depth. Okay? So they're going to tell you what the depth is. They're going to say it's a function of r, which makes sense. It should be different depths depending on how far we go away from center. And they are going to tell me that it is 13. The depth is 0.115 e raised to the negative 2r millimeters. So my input here is a distance in kilometers. My output is going to be a measurement in millimeters. Okay. So we want to find the total volume of the soot in the first 5 kilometers away from this thing. Okay. All right. So I don't know how to do this. So I got to cut a slice. Some sort of slice where over that slice the depth isn't changing very much. Some sort of slice where my function here is a constant if I look at a thin enough slice. Well, this is what my slice is going to have to look like. Because as long as I don't change the radius very much, then my function is about constant. The depth is constant in that little ring. So that's my slice here. Okay. So what I can think about is, what is the total amount of soot, maybe, in that one little slice? Well, it should be the depth in that slice. Here's my depth, times the area of the slice. Does that make sense as a setup? Depth times area should give me a volume. That's what I'm looking for. I'm looking for a volume of the soot. So maybe I should even change this from S to V, because I really am looking for a volume of soot here. Volume of soot. So far, so good? All right, now I just got to figure out what this delta A is. But it's a circle. It's a little weird. So one way to think about this is to take your scissors. Right. Those are scissors. Right? Cut my circle. Right, I have my circle like this. I cut it, and I roll it out. Right, when I cut it and roll it out, it's going to look like this. I say, great, it's almost going to look like a rectangle. I know how to find the area of rectangles. I just take the length times the width. In this case, what will this thickness be? Delta R, so it'll change in the radius. And what will this piece be? Circumference of that circle, so that will be 2 pi r. So in this case, my delta A turns out to be 2 pi r times delta r. And this should give me the volume in just one little slice. Now I want to find the total volume. Total volume is the integral of all this stuff. So there's my h of r, 2 pi r dr, integrating from 0 out to 5 kilometers. And I just integrate this thing. Looks kind of ugly, but when you factor out the fact that I have just ugly constants, it's really like r times e to the negative 2r. That's going to be integration by parts problem. Now, there's probably a lot of people out there who said, I got this right. And then I went to put in my number value for the next piece, and I got that wrong. How can that be? How can I have the right integral and the wrong output? And the reason is because of our units. We got to be careful about our units here. In the end, in Wiley, they're going to say, okay, next evaluate this and put your number in here, and then they'll put meters cubed right there. We have to think about what units we got. So far, this expression, whatever number I get from this, if I think about the units, it's going to be kilometers. And we can kind of think of this as having kilometers. It really actually doesn't. This is really the notation that goes with the integral. But our limits of integration are in terms of kilometers. Right? A lot of people will say, if this is in kilometers, but it's infinitesimal, how does that work? Right? Well, really, this is the notation for the integral, but the limits are talking about kilometers. So I'm getting units of kilometers from the integration, kilometers here, and millimeters here. So whatever number this kicks out, it's going to be 12 in the units of millimeters, kilometers, and kilometers. And I got to convert that to meters cubed. So I say, how do I convert from meters or from millimeters to meters? I'll have to think. I'll do the conversion, right? If I'm taking a millimeter and I'm multiplying it by something to get a meter, I want a millimeter in the denominator and I want to get a meter in the numerator. I know that 1 meter is 1,000 millimeters. Looks like I'm divided by 1,000 there. So I divide by 1,000 here. Kilometers I'll have to multiply by 1,000 and multiply by 1,000. And when I simplify that, it looks like I have to take my answer and multiply by 1,000 to convert from whatever this weird unit is to meters cubed. Okay? Any questions about that one? Was the problem the setup or the units? Okay, yeah. Gotcha. It's a tricky one. Units are important though, right? Annoying, but important. All right, other questions? Yep. 21. All right, a rod with density. A rod with density, which is equal to 2 plus sine of x, lies on the x-axis between 0 and pi. So I have my x-axis here. I have my thin rod that goes like this. All right. And it ends right here at pi. And that's its density. Find the center of mass of the rod. Okay. So, and generally we're going to have to integrate x times the mass and divide it by the total mass. And here's the weird thing. I don't see in the book anyway the units for the density. That's kind of annoying. Because depending on what units they give me, I should kind of have to adjust for that. I guess it's a thin metal rod, so there must be no volume to it. So I'm going to assume this is going to be grams per meter or something like that. And so my dm is just going to be density times distance. So I could really turn this piece into density times distance like this. So density times distance. And I'm a little annoyed that they don't have the units in there because they really should. But at the same time, I can go through this process and do this integration, but I'm going to find out that the center of mass is at pi over 2. I can really just look at this and tell that that's going to happen. Why is that? The mass is not constant. Our density is a function of x. Our density changes. It is less dense here than it is here. Right. The sign of x there is going to be symmetric along this spot, right? If I draw a picture of the sign, it's going to look like this. So the density is changing. The mass is changing. It is less dense here than it is here. But the density here is going to be exactly the density here. And the density here is going to be exactly the density here. So it's absolutely symmetric about the center of this object. So because of that symmetry, I really know the middle is going to be the middle here. Okay. So we can look at this problem and see that. Now, of course, if we don't see that, we can still go through the integral. It'll be fine. We integrate both of those things from 0 to pi, and we'll get our value. Okay? That help? Good. All right. All right, I got about 10 minutes left, and I do want to get into 8.5, so I'm going to start 8.5 here. And I think, once again, because we've been setting up all our problems in terms of those slices, I think we'll be okay kind of going through the concepts quickly and really hitting up a bunch of problems on Monday. There's two topics we really want to hit in this section. Work, which is a measure of effective force, and force and pressure. Those are the two big ideas. And we have kind of our big formulas from these sections. So you went through the video, you watched the section. The highlights are here. These different formulas that we're going to talk about and how we're going to use those to find this thing, these different values. All right, so these are all our big formulas. We want to talk about in section 8.5. So we're going to start off with work. and an idea of when we need to use integration. So we just said that we have work is equal to the integral of some function dx. But wait a second, I've had another formula for work. In this course, we've also given another formula for work. What was our other formula for work? Force dotted with displacement as a vector, like this. Why two definitions? And in fact, these aren't the only definitions. There's going to be another one you're going to see later. And it really brings us to the fact of when do we need to use integration. That first definition for work is absolutely valid. It says that if I have some sort of my chair here, and for whatever reason my chair is moving in this direction, but I'm applying a force in this direction, like maybe it's against a rail, and I'm pushing like this, and it's sliding in this direction, like this, then the actual work is going to be a little bit different than just the force times the distance, because my force isn't in the same direction as the motion. So there's going to be some sort of scalar change there. It's going to be that cosine of theta. But when I do this calculation, I'm assuming a couple things. One, I'm assuming that my force is constant. It is not changing at different times. I am a robot that is just kind of walking along this path here and not changing at all. And it also assumes that my displacement is constant, that I am moving in this vector direction and I am not changing from that vector direction. Of course, that's not how work works all the time, right? Maybe if I'm pushing my chair across, I might go fast and I might go slow. The force that I'm applying to my chair is now changing as I move. It's a function. It's a function of x. So how do I account for that? Well, that's what we look at in the next one. Now we're using integral because I won't be able to calculate the work all at once. But if I look at a small enough slice, one little step, if I go from here to here, that force that I applied in that little step should be constant. And then I should have my force times my distance to get the work in that little step. And I can find the work in this step, and this step, and this step. And I can add them all up continuously using my integral. Now, I guess there's one other extension of that. We said in the first case we have force and displacement were both constant, but they could be going like this. And now I have an integral representation. I'm talking about me moving my chair here, but I'm actually aligned here. That force and that dx are in the same direction. So the last option would be, what if my force is not a constant if it's a function, but also the motion is also not constant? Now I'm going like this. I may be a particle traveling in some sort of magnetic field. That would be multiple integration tools, and that's what you talk about in Calc 3. So work really extends across many levels. We have a vector definition, we have an integral definition. Later on, you'll get a more of a vector calculus definition. All right. So that's kind of the tier. So we talked about two so far in this course. You'll talk about one in the next course. And you want to try to be able to tie all those together. All right, the other big warning here is about units of force. This is something that always trips us up on our homework, the difference between mass and weight. Right, mass and weight are not the same. Mass is the amount of matter, and weight is the force that you get when you apply the force of gravity to a mass. So force is a mass times a gravity. And so that's kind of that conversion here. So they will be different. Now in general, we're going to talk about weight densities and mass densities. And so you should know there's a little bit different. If I talk about the kilograms per cubic meter, that's a mass density. The result is a mass, not a force. If I talk about a weight density, pounds per cubic feet, that is a force as a result. Right? If we take that value, if I take pounds per cubic feet and I multiply it by a volume, the result is a force. It's a weight. It's not a mass. Okay? So I'm going to highlight those differences and we'll see their effects and problems here. All right. When calculating work, we really have two flavors of problems. And I have some sweet pictures to represent both of those flavors. Okay? We have what really fits our formula well. Work equals some function times dx. We're going to integrate. I'm going to call this the chain problem. I have some dude here at the top of a building, and he's holding this big long chain, and he's hauling this chain up. And of course, as he pulls this chain up, he's doing a certain amount of work, and we want to calculate how much work he's doing here. Okay. Now, what's the force he has to apply? He's fighting against gravity. He's pulling up the weight of this chain. So it's really the weight that he's counteracting. So his magnitudes will be the same. So he's counting up the weight, essentially. But there's a problem. We're going to try to leave our cheesy mathematical examples. And so this isn't going to be a chain of no weight and no thickness and no dimension. It's going to be a real chain. And the real chain is going to have some sort of weight to it, which means the weight that he's pulling as he pulls up is going to be changing. The force that he's going to have to use is going to be different as he pulls his chain up. It's going to be a lot heavier right now than it is when he's almost to the top and there's only like a foot of chain left. Okay, he's going to be carrying a lot less chain. So the weight is going to be changing as he pulls it up, which makes it an integral problem. Okay. All right, so how do we do this thing here? What I want to do is find the work it takes him to just take this chain and move it one little motion up. All right, so we're going to think about one little slice of the work here. So our work is really force times distance, which is the weight of this thing times the distance. So we got to figure out how much weight he's pulling up. It looks like there's an anchor at the bottom here. That's going to give us a standard 100 pounds. And after that, that chain weighs 3 pounds per foot. Okay. So we have to think about what happens after he pulls it up some random distance. So let's say from the bottom here, he pulls it up some distance of x, up to some random spot. And now from this spot, he's going to pull it up just a little bit farther. And we want to find the work he calculates to pull that little bit farther. Okay? And so it's going to be the weight times that little bit of distance. So first of all, what's that little bit of distance he's going to pull it? Delta x. All right, so that's the distance over here. Now, what's the weight that he's pulling at that point? Sort of. Depends on what we called x. I didn't call x the distance from the top down. I called x the distance from the bottom up. Yep. It depends on what we want to call it, right? I probably should use y here. That's more natural when we're counting vertically, right? I'm not really on a coordinate system here. I'm just calling it some distance as a variable. But you're right. I should try to make it a little less confusing, right? And use y as a good variable for things that go up and down. So absolutely. Okay. All right, so what about the weight? It's not 3 times y. It's 3 times what? 25 minus y. So I have 25 minus y. Now, I certainly could change that just by defining my variable differently and just have it in this case. And that should represent the work it takes, the weight of that thing, no matter where I'm at in this process. That represents the work it takes to move this some little distance y at any point along the process. So then to find the total work, I just add up all those slices. So I'll get 100 plus 3, I'll distribute that 3, so I'll get 175 minus 3y dy, integrating this thing from, it's like 0 to 25. Now be this problem. And I should think of the units here. I will have units of work. So units of work tend to be, what do they tend to be? Newton meters? Joules, yes, Newton meters, which are joules. That would be for the metric system. Now we're in standard foot pounds. Yeah, absolutely. So, and that's what I should have here because I have all this quantity inside here should just be a measure of pounds, right? Because I have 175 minus my piece over here. This is all just the weight. No, this is the weight plus some weight density here. 3 pounds per foot. That's weight. This is all weight. This is all pounds times some change in feet. So it will be foot pounds. All right, so that's the first problem. The second problem we're going to do, I'm going to sketch it real quick here. I need to find the work it takes to empty this tank of water. And so here's the concept behind it. I don't know how to do it all at once, but what I want to think about is if it just take one little slice, like this, and I move it some distance to the top. If I move it that distance, I should be good. So what I want to find is the weight in that slice times that distance. That should be the work it takes to move that slice out of here, and it'll add up all those slices. So that's a problem. That's a process. See if you can get through one of those, and we'll start class next time with this problem. All right, next time we're going to talk all about 8.5, a lot of practice examples, and I will hopefully send out a practice exam sometime shortly.